Okay, hello everybody. Welcome to the new format for Linguistics 341 for the rest of the semester. Today I'm going to talk about resonance. We're going to just follow up on what we talked about last time about harmonics. Based on some recommendations I've gotten from the internet, I'm going to try to kind of break the whole resonance lecture down into subparts. And actually the strategy I'm going to use is I'm going to stop wherever I have like a question in the lecture notes that I normally use. And that'll give you some time to kind of think about the answer to the question before you start on a new video. So other than that, I'm going to leave the announcements and such to offline, not in these videos. And with that in mind, I'm just going to kind of get into it. So last time when we were talking about harmonics, we crucially learned one very important fact, which is that the component harmonics of any complex periodic wave all have a frequency that is an integer multiple of the fundamental frequency of the complex wave. So hopefully you recall, like if the fundamental frequency of a wave is 100 hertz, we only are going to get harmonics like at 100 hertz, 200 hertz, 300 hertz, so on and so forth. And then at the very end of class, we had a little demo where I pieced together what sounded like speech out of just 3 sine wave harmonics. And I'm going to do that again in a slightly different way. Whoops, wrong option there. So I'm just going to create a sound from a formula in Prot. I'm going to put sine waves at 300 hertz. Hopefully you can see this okay. I'm going to post these notes in a couple of different formats online, one of which is on YouTube, which is usually not that great for resolution or clarity, and also on my personal website, which is usually gives me the opportunity to post higher quality videos. But what I've got here, as I'm walking through this, is a complex sound wave, which is going to be composed of sine waves at 300 hertz, at 2100 hertz, and at 3300 hertz. So I'll put that in the name of this creature as well. And I'll point out as I do so that I'm also changing the amplitudes of these sine waves a little bit. I didn't do that in class the other day. So the lowest frequency one is the highest amplitude. The peak amplitude is 1/2. And the second highest frequency, or the middle frequency, has a peak amplitude of 1/10. And the highest frequency sine wave has a peak amplitude of 1/20 or 0.05. I'll just create this, double check that my sound is working. Yeah, so you should be able to hear this okay. We'll play it first. And I'm going to tweak this a little bit so that we can see the harmonics better in the spectrogram view. And I'm going to turn off pitch as well. So up here at the top, again, we have the waveform view of this complex wave. It looks a little bit different from what I showed you in class. It's got these nice little jagged edges, like an Alanis Morissette album. But that doesn't matter to us so much as what's going on down here in the spectrogram view. So this is showing us time in the x-axis, or the x dimension, the horizontal axis, the x dimension, and then this is the frequency scale on the y-axis. You can't really see variations that well at this point in the z dimension here, which is represented by sort of differences in shading. So the darker these lines, the more intense they should be. I haven't really created a complex wave where you can see that really clearly. The main point I want to show to you now at this point is that if I click on these sine waves, I should see the frequencies that I constructed them out of. So this is at about 300 hertz here on the frequency scale. This is about 2100 hertz, and this one's at 3300 hertz or so. And when I play it, you might have to use your imagination a little bit, but the vowel it should sound like more or less is the vowel E. So high front tense vowel. How did we do that? All we have are 3 different sine waves in here. We can do a little better than that, it turns out. So I'm going to play some examples from an experiment that was run about 40 years ago now. So this is run at the Haskins Lab in Yale in Connecticut. You can tell me what you hear out of this, if anything. So usually this is the point in class where people kind of like their ears perk up and they think that they might have heard something. I'll play this again. So perhaps you heard this when that was playing.
Where were you a year ago?
Okay, I'll play a couple more demos. That one didn't play all the way through, so I'll play it again. Let me try it. Yeah, it's supposed to, for some reason my computer doesn't want to play these sound files all the way. This is what the original sounds like.
Kick the ball straight and follow through.
So it actually, you said the word through there at the very end. It actually followed through on what it was trying to say. I'll play that sine wave version again. Through. And here's the last example. It's very frustrating that this isn't working. So that, I don't know if you're able to decipher that one, but this is the original.
The steady drip is worse than a drenching rain.
Yeah, so I'll play the sine wave version again. So it should say drenching rain at the end there. I'll show you these spectrograms for these guys in a minute, but basically what's going on here is that these are complex waves that just consist of 3 different sine waves each, and you're just changing basically the frequency of the sine waves to give you that percept of speech. The example I played for you at the start, the sine waves do not change frequency or anything else as they go throughout this entire complex wave. So it sounds comparatively boring, and it just kind of sounds barely like speech, but you can get it if you want to. It's easier to get the speech percept for these guys. Okay, so let's review here for a second what we've got. One of the interesting things that's going on in these, before I forget, is that one of the characteristic features of speech sounds is that they exhibit spectral change over time. I'll explain what that means in a second. But yeah, actually I'll go back now that I'm thinking about it. And let me open up a sound file from, let's say, the production exercise, which was actually grading earlier today. So you can see from one of the originals here what I mean by spectral change over time. So here's a fun one. Okay, so with a spectrum, this one's going to be a little bit noisy, but I'll grab a spectral slice from the middle of this sound file. I think this is from the vowel O. All right, so I just created a power spectrum from that particular slice of speech. And if you recall, what we see in a power spectrum are the harmonics of a speech sound. So this one's complex. It's a lot more complex than what we've seen before. But basically, just to remind you, what we get here is on the y-axis, we have intensity, and on the x-axis, we're plotting frequency. And this is another reminder of what we learned about harmonics last time, is that these guys should all be integer multiples of each other. The frequencies of these guys should all be integer multiples. This is about 222. This one should be about 444. This one should be about 666, so on and so forth, all the way up the scale. It's a little bit off, but you kind of get the idea. That's just a reminder, though, on the y-axis for a spectrum is intensity, measured in decibels. On the x-axis is frequency, measured in hertz. So that's what we can. That's how we can analyze a complex sound. What I was saying about how speech reflects spectral change over time is that those spectral characteristics, the specific harmonics we get in a spectrum, are going to change as a person speaks, as their flow of speech exits their mouth, right? So if we look at the spectral slice a little bit further down the line for this particular stretch of speech, it's going to be slightly different from the one we got the first time. So this is a few milliseconds later. This is what that one sounds like. That one sounds a little bit different, but the main thing is, maybe I should squeeze these spectral patterns, the specific harmonics you get at specific frequencies are going to be different at different points in time. Okay, so these two power spectra do not match up exactly, even though they kind of sound the same and they kind of look the same. Okay, so where does this leave us? So remember, at kind of the base of any sort of periodic sound, at least in speech, we've normally got the trilling of the vocal folds, creating a complex wave that has a fundamental frequency. That complex wave, just by virtue of being complex, is going to consist of a series of harmonics. Those harmonics will all be spaced apart from each other on the frequency scale of one of those spectra by the fundamental frequency of the complex wave. So your vocal folds are opening and closing at a specific rate, like maybe 100 times a second, maybe 200 times a second, what have you. Their harmonics are going to be multiples of that fundamental frequency. So as a guy, I might be likely to produce speech at 100 hertz frequency, fundamental frequency. The harmonics I produce for a complex wave with that fundamental frequency are going to be at 100, 200, 300, 400, and so on and so forth. A female speaker, an adult female speaker, might be more likely to produce speech with an F0 of 200. So her harmonics would be at 200 hertz, 400 hertz, 600 hertz, so on and so forth. We can't change those frequencies of the harmonics independently of each other. If the fundamental frequency, if the F0 is at 100 hertz, the next one's going to be at 200, the next one's going to be 300, so on and so forth. So when I say we get spectral changes in speech, if we can't change the frequencies independently of each other, what else can we change? Answer coming up in the next video.